Hello, we are the Drone Undercarriage Delivery System, or DUDS. I'm Natalia Kelly, and in the group as well as Nicholas Bands and Brayman Twitchell. This is our final presentation for AE 401. For a brief overview, we're going to go over the objective and key question of our experiment. We'll then be going over the background of why this experiment is relevant and some of the methods and research that we did to establish the experiment. We'll then be going over the methods that we use to conduct the experiment, as well as our results, and then the final conclusions and implications of our results.
So first off, we have our objectives and key question. The objectives that we were trying to accomplish were to compare efficiency of varying undercarriage designs and compare these to the control efficiency of just the drone itself. Our goal was to create a stable testing method for future designs, if there are any. And then we also want to find an optimal undercarriage design based on the three that we created. Our key question that we're trying to answer is, what is the optimal design for a drone undercarriage to maximize efficiency? In order to answer this question, we conducted velocity testing with the drone outside.
Just for a little background, so Amazon had 9 billion sales in 2024 and had a goal of eventually delivering 500 million packages annually by drone. NASA also works with drones that have a tethered or external attachment delivery system, and both of these work to create a market for the undercarriage delivery systems in their expansion of future drone packages. And drones carrying packages underneath is also the main focus. So the undercarriages are designed to carry these packages and to deliver them efficiently. This design focuses on the way that drones carry packages with the goal of making it more efficient and aerodynamic overall. That's why we're testing so many different models. And it matters because if successful, companies can use the system to deliver packages across the world, and especially in this expanding delivery platform. This is our drone here. It was about $45 on Amazon. It is the drone with 1080p camera. This drone forced us to scale all of the packages and testing to a certain size, although the results are all applicable to a larger drone that would be more used with NASA or Amazon.
Next, we're going to talk about the designs we've came up with for undercarriage system. So this is the SolidWorks models of our designs. I'll talk about more in the next slide here. So right now we have, these are the printed designs. So as you can see, the first design is a NACA 23015 blade. This is a full blade with a hollow inside to put the quarters in, which we use to mimic our weight. And then next we have design 2, which is going to be attached directly to the underbelly of the drone with a hollow inside, sort of like a bowl to hold the package. And then design 3 originally was there to be designed so that it attaches vertically on top of the drone.
So our final designs are a little bit different than the original ones. The first design was too heavy, so we got rid of the main body of it and replaced that with paper, and we used more paper inside it in order to make it stiffer and more stable. Design 2 was light enough that we were able to use it with the drone, and so that remained the same. And then design 3 was too big, too heavy, and wasn't properly fitted to the drone, so there were complications with both the propellers and the propeller arms. So that was scrapped, and design 3 is now a cotton material. It's a fitted design that forms to the shape of the package as well as the drone.
Next, we're going to talk about our test plan. So the first thing we have to do is acquire the drone and then get control of the drone. So like the drone without any delivery system on it and the speed of that. And then we create a scaled weight and model package for delivery system based off Amazon's. Then we did how to do 3D print multiple designs as you saw before. And then to get to the actual experiment, we got to measure the speed of the drone with the delivery systems from point A to B, which we'll explain farther later. And then vary the drone undercarriage designs and repeat the previous step. And then once we get all the data, analyze each test and determine which one is more efficient.
Our revised test plan involved doing preliminary control testing beforehand while we were waiting for our designs to print. We conducted the tests outside in order to test for speed, and we decided to not do any endurance testing as we were running low on time, and it would take too long to do that and the speed testing. We also shortened our flight distance. It wasn't originally 600 meters, and we switched it to 25 meters. We also revised where we were putting some of the undercarriages because of what we thought was a sensor issue. There's a sensor underneath the drone that helps it land, so we thought that was an issue with we were just blocking it, but it was more so a weight issue and low battery. So that led to us revising some of the designs. We made some of them lighter. We changed one completely, as you saw, and then the other one was light enough and didn't interfere with the sensor, as it turned out.
Next, we'll be going over the schedule. As you can see here, there's just different weeks. So the week started when we first started our first assignment. And so we can see here how we had a plan. As you can see, a very left column, that's when we planned to start. And then in the second and the third column, that's when we actually started. It was pretty on par. The biggest things was waiting for the 3D printing to come out. We didn't anticipate it to be that long for everything to get 3D printed. And then for the speed testing, we had to wait a week because we couldn't find a day that we were all available and the weather was good.
For our risk assessment variables and controls, variables that we had to deal with were the wind, the battery life of the drone, and also just human error, whether it's with timing or saying when to start or stop. Some controls that we had were we would fly the drone in the same direction each time in order to keep it consistent with the wind and whatnot. That included flying the drone facing backwards as opposed to forwards just because it was faster. For risk assessment, we had weather being an issue. If the weather was bad, we just decided not to test that day or to try to test inside, which we never ended up doing. Injury caused by the drone if it were to crash into one of us because we're not professional drone pilots. That was never an issue, but it's something we considered, and there were guards on the drone in order to help mitigate that risk. And then impact damage from the drone or on the drone if it were to somehow get flung into the trees or into the building. And then if it just like damaged something on the ground or whatnot. So that was another risk that we had to keep in mind.
Going into our test equipment, we had the drone we acquired on Amazon mentioned earlier. We then used the 3D printers with 0.02 tolerance of filament size. Then we also had the scale that we used to measure all the equipment, the stopwatch, and small packages that we scaled to the size of the drone and thrust. The drone was the only cost, and it was $45.
So this is like the design of our experiment. So what we decided to do is go behind more. Originally, we were going to do it at Baghdad Field, but it was just way too open, too much wind at all times, so we couldn't get any good data. Behind more, there's a big building, so it kind of blocked the wind. So we measured out. We measured from a tree to tree, and it was 25 meters. The temperature for that was 68 degrees Fahrenheit, and the wind was 7 knots, and it was attacking. It was against the way we were flying the drone as well, which also impacted our data a little bit.
So going over some of the results, the fitted design of the highest efficiency, the half airfoil NACA 0018 was a close competitor. That was the second design. And then the NACA 23015 was the least efficient. All results had significant differences from the control times as well. So the drone had the fastest flight time with 4.05 average flight time for 25 meters. The other times came out to be with the NACA 0018 and the fitted design having very close results, and then the NACA 23015 having the least efficient results. This comes down to showing that if extended for a larger period, the flight times would be significantly different when you talk about the overall flight times that are considered in actual results for Amazon packages or NASA. Figure 1 here shows the velocity averages per design. Again, this shows that the fitted design had the best performance in comparison to the drone. And then the NACA's 0018 had the second most efficient, and then the NACA's 23015 had the third least efficient. This also comes down to those extended results and being able to maintain a steady velocity and being able to expend less energy to deliver one package.
In conclusion, obviously the fitted design had the best performance, as mentioned previously, and the NACA 23015 airfoil design was the least efficient, just barely though. It was very, very close throughout. In the future, we suggest further testing, whether it be indoor or outdoor. Indoor would probably be better, though, like environmentally and like real world conditions, it's going to be outdoor, but indoor testing will allow it to be consistent. There's going to be no issues with wind or variations in temperature or whatnot. So it'll help keep results consistent and equally matched.
Then these are the references that we're able to use to kind of give background on our project and kind of based on where we wanted to go and what we were looking for. Thank you, and hope you enjoyed our presentation. If you have any questions, please feel free to reach out.